about going into next were modal formulas or linear logic or Rolang stuff. What are you in the mood for?
Well, I'm waiting for your rhoxy.
Oh, I'd be happy to start with that. Yeah, definitely. I think Isaac is, or at least maybe you and Isaac are the right people for modal logic stuff.
Isaac, definitely.
Okay. Oh yeah, I do want to watch this though. I didn't realize Christian had given this talk already. I'm glad Gary.
Oh yeah. I started and I definitely looking forward to watch it multiple times.
Oh yeah, awesome. Yeah, Christian. Oh, you were in those RCLs when he was there.
Yeah.
Okay, so hi Gary.
Maybe he can join us sometimes here for some explanation about category theory.
Yeah, Christian, that would be awesome.
Yeah.
Yeah. So, okay, I don't know exactly where to start here, but I'm sure that once we just dive in, there'll be cool things to show. So as I mentioned before, I started over in JavaScript. And well, maybe we'll take a quick look at the parser and go from there.
Mm-hmm.
So here's what I parsed so far. Any ground terms so far, I have integers, nil, and I think maybe tuples. Oh no, bools and strings, no tuples. Nil, int, bool, and string are the three ground terms I have. And I represent, it's all deep encoding. So I represent all of my ASTs as nested, like as JSON basically. But then once I get in the evaluator, they're not strictly JSON anymore because they start to have some like methods, but they're always just JavaScript objects. And the ground terms always look like this. It'll be like tag, ground, type, int, for example, value, and then like just an actual JavaScript integer, or in the one special case, nil is just this, its value is just the string nil. So back in here, so okay, so I've got ground terms. This is just the bracket one, allows me to parse a process with the, angle braces. We have a send, receive, par, and bundle, and new.
Oh, nice.
Yeah, so bundles are not the full-featured bundles that they are in co-op Rolang. They do this job where you can't pull them. Well, they honestly don't do anything yet. But my vision is that they'll do this job where you can't pull them apart by like pattern matching and pulling out the guts. But I'm not yet setting out to do this like bundle plus where you can only write on it kind of thing.
And are the bundle just like labels on the processes?
Yeah,
you just label the process. This is like a special kind of process. You can do these kind of things, and other you don't.
Exactly. And so here's the AST. It's, remember, like I said, it's always a JavaScript object. So its tag is bundle, and then the second thing is the key is proc, and the value is whatever actual process we parsed from inside that bundle. So it's basically just like a wrapper, a labeled wrapper around the process.
Okay.
And the purpose is this, like whenever you try to evaluate it or check it for structural equivalence with anything, you just unwrap it and use the thing inside. But whenever you try to pattern match on it, it says like, the pattern match fails, like it just doesn't match. So those semantics I don't expect to be very hard to implement. And then new is new. Oh, so these are, the double underscore is mandatory space and the single is optional space. And so, and they both include comments. So I'll show you that too. So like,
cool.
We've got, well, yeah, I mean, basically, the optional one is 0 or more white space characters, and the double underscore is 1 or more, and then a white space character is, it makes sense. Space tab, new line, vertical tab. I don't know what F is, but I just copied that from an example. And then I've also added in block comments and line comments.
Cool.
Joshi, could you tell me again, what is rhoxy?
Oh, totally. Yeah, rhoxy is my spin on Rolang. It's basically Rolang with a couple things that I thought I wanted to do a different way changed.
And so you wrote it in you started from the grammar.
Yeah, exactly. So what I'm showing, like big picture, what I'm showing here is a JavaScript project that is an interpreter for rhoxy, which again is basically Rolang. And so to zoom in, right now I'm showing us this part, which is in source parser, and this is how I'm parsing the syntax for rhoxy. Wait, where was I? Roxy that. So that's pretty much all the grammar. Oh yeah, right. So Gary, one of the big things that's different about Roxy than co-op's Rolang is that there's no distinction between processes and channels. There's only processes. But in order to preserve the syntax, one thing I want is for code that was written for co-op Rolang to still run in Roxy. In the places where you expect a channel, you parse it like this. You just look for an @ sign and then you parse the process. And all you end up giving back is what I called C, which is just the process itself. So although you need to type a literal @ into the syntax, it still is just parsed as the underlying process. None of this stuff, this basically it parses correctly. There's one parse ambiguity that I need to fix still. That's what my to-do is. But I know that if I just take the first of the two valid results, it's always the one I want. And so that's what that's a little technical debt that I'll have to pay back later. So maybe then the next best place to start is, okay, so I'm closing the parser folder. Now we're just exploring source, and this file is rhovm.js. So this is where most of the magic happens. Just to orient everybody, there's also helpers.js, which has things like a function to check whether two processes are structurally equivalent, and a process called evaluate in environment, which takes something like @x send y and evaluates x and y based on what they were bound to earlier and gives you back a fully concrete tree for that same send and things like that.
So can you show us this?
Oh sure, yeah. You want to start there?
Yeah.
So here's evaluate an environment. I'll let you read the docs.
So I'm interested in the environment.
Yeah, so the environment's just a map. It's a map from variable names to whatever they were bound to. And so we go, this is a recursive function that, recurses down the tree and looks up anything that needs to be looked up. So
you have, sorry, I will interrupt you.
Yeah, please do. That's great. Yeah.
So you have global map of free variables. Can I say like that?
No, it's not. It's not global. It works like, well, okay. So let me start over here.
It's like a based on scope, right?
Yeah, there's closures. It's lexically scoped. So every time a receive process gets parred into the tuple space, if it happens manually by me deploying for whatever from @nil, then do some continuation, then that's a pretty simple closure. It doesn't have any bindings to begin with. And so when I call deploy, all right, so let me start here and we'll work back toward helpers. And I think that might.
Okay, yeah, sure.
So this is called fresh. It creates a fresh rhovm, and this is the thing that's exported from my rhovm module. So when you're gonna create one of these, you start by making a fresh instance of the rhovm. And to make a fresh one, you have to give it a few parameters, which it's fine if both of these are just empty JavaScript objects, but it is initial registry entries and I call them FFIs. It's like functions in the foreign function interface. So for a simple tuple space, these will both be empty and we don't need to think about them. But in a more interesting tuple space, we might have these registry entries, which are, it's basically a map from string URIs to just like numeric identifiers. Every term in my tuple space has what's called a process ID, and that's basically what these are doing.
Okay.
So, and then here's the actual functions themselves. So it's a list, and it only has a single comma in here. So it's got two functions in it. So here's one of them. Sorry, here's one of them. It's a join, and the star means it's a special join that's going to do some like, it's going to, instead of being handled fully by the row VM semantics, we're going to hand off to JavaScript at some point is what the star means. And so with a normal join, you would have persistence, you would have actions, that all looks the same. And where it's different is body. So for a normal join, body would just be another JavaScript object that's like probably a par, you know, but it's whatever the continuation is. But in one of these join stars, body is a function that just takes in some bindings and then does some JavaScript stuff. So like this one is, wait, I think, oh yeah, this one's standard out. So it's pretty simple. Like when you call this one, all it does is console.log whatever message you sent. And then same thing down here for standard error, except it does console.error instead.
And the bindings that you're getting in the body is from, you're saying bindings get MSG. So
yep,
you're searching this map in the environment.
Yep, that's right. And for this particular join, so bindings is something that always gets created when you do a COM, right? You have some send and some receive, and that receive is going to create some bindings. Like if it's a simple one like for X from some channel, then X binds to whatever thing you sent. If it's, you know, if it's more complicated, if it's for some complicated pattern from whatever, then you might get a bunch of bindings. And since these ones are standard out, you're expected, in fact, you can look at the action right here. It's a for message from, you know, whatever the proper unforgeable idea that's mapped to standard error, row IO standard error is. So this is like, you know, for message from standard error. So message is going to get bound to whatever was sent. And so that's the only binding. This is going to be a map with a single key value pair.
And with the name, a given name, right?
Exactly. Yes, with whatever came from, whatever you called it in the action. Yeah.
And here you are defining, right? You are defining the name here directly.
Totally. Yep. Totally.
You are building a part of the AST, right? And
totally. Yep. This, I just manually wrote this AST because there's only a handful of them, but this looks almost identical to what would have been parsed if I had actually written row length syntax.
So in a sense, you're using the real name, but this is okay for you.
Oh, that's right. I haven't done anything with De Bruijn indices anywhere, and I'm not sure that I'm going to have to.
This is cool.
I'm still open to that idea. Yeah.
This is cool. Yeah.
Yeah. Okay. Cool. Yeah. Thanks. So let's see how it plays out. Okay. So we create a fresh row VM, and then the registry is pretty clear here. If you didn't give me any initial registries, just initialize it to an empty map. Otherwise, you know, use whatever registry entries you gave me. These three things represent the tuple space. And so my data schema is a little bit funny. Let me, I wrote an example over here in the README. So here's kind of how a tuple space works. It has three parts, and they're all three maps. So prox is a map that goes from some unique process ID to the actual AST, whatever it is. And you'll notice it doesn't matter whether it sends or joins, they all go in here. Both of them go in here. So this is basically just like a map by ID of every process that's in the tuple space. And what that allows me to do is when I'm specifying a specific COM event that I want to execute. So this is basically like what replay rspace does. I'll say like, I want to execute a specific COM of process 1, 2, 3, and I want it to COM with process 5, 6, 7. So when I specify the COM that way, I can quickly look up the processes and in constant time, actually, and execute them.
Cool.
But I also want to have this function that like auto reduces. You know, I don't want to manually specify every COM of every program that I run. I want it to in most cases, except when I'm debugging or replaying, I want it to just automatically find COMs and execute them. So I also want to do the more traditional thing where we have a map from like a specific channel to all of the different processes that are sending on that channel. And then likewise, from a specific channel to all of the processes that are listening on that channel.
Can you clarify this a little bit?
Yeah. Basically, let me tell you the goal first. Okay. I want my lookups, when I want to look something up in the tuple space, I want it to be fast, ideally constant time, regardless of whether I'm looking up by a process ID or just by a channel. If I'm just saying like, hey, give me any send that's listening on this particular channel. Now, if I only specified the tuple space this way, which is what we've talked about in the past, then there's not a fast way to look up by process index. I'd have to go O of N through, first of all, every channel and then every process. Oh, wait, is that true? Oh, yeah, and then every process on that channel until I find the right ID.
So in prox map, you have all the names. All the names are in the prox, right?
In all of the processes that are in the tuple space are in this map. Yeah. Yeah.
And so when you're searching for two names to have a com, mm-hmm. you can find it in prox. You can search the first name, and you can search the second name and see if they are a match, right?
Oh yeah, like I could just look at these two and say like, is one a send and one a join, and are they on the same channel, and do the patterns match? And if not, then I could go on to first and third, first and fourth, then second and third, second and fourth. Yeah, totally, I could do that, yeah. But the problem is it's O of N squared to do that.
Oh, okay.
You know what I mean?
Oh, so so you have these additional maps to with different keys, so you can.
Bingo.
And these different keys are combined keys for multiple names, or I'm very much interested in that.
Yeah. Okay. Yeah. So let's say I'm going to put a send into the tuple space, right? I'm just going to par in at whatever sends something. That's going to go into two different places. It's the easy one is it's going to go in here. All the sends and joins go in here. Done. The second part is when I put a send, if it, imagine it's like at chan1 send 5, then I'm going to go into my sends map. I'm going to find the chan1 key, and I'm going to add this send that I just put into the set of all sends that are sending on chan1.
Okay.
So when you put in a send, it goes in two places. It goes in the big free for all where everything goes. And then it also goes in the correct channel-based spot in the sends map.
And here the value of this map is a set.
It's a set. Bingo.
Not only the. So you're just the first time you will create this key with only singleton element, and the second time you will add it to this set.
Bingo. That's right.
Okay.
And joins work basically the same way, but there's this subtlety in my example. So like if you look up here, you'll notice there's only one join in the tuple space right now. Its process ID is 567, but that's actually in two different spots down here. And the reason is that joins can listen on more than one channel. This is like 4x from chan1, semicolon y from chan2. And so it's listening on both of these, and so it goes into both spots.
Okay. And now when you're searching for com event, you don't have to look at the prox, right? You just...
That's right. That's right. So I actually haven't written the part that looks for com events yet. I only reduce them when I specify them manually. But my plan is this. Go into the joins map, pick out, whichever join you come to first. In this case, it's obviously going to be the only one that's in there. Look at all the actions on that join. In this case, it's 2. There are 2 actions. And then for each action, see if there's a send that will send on that correct channel. And that's a super easy question to ask. Is there a send on the right channel? Easy peasy. Go to the sends map, go to the right channel, see if its set isn't empty. And now you've got a send that'll work there.
Oh, in a sense you have, in a sense, and joins, when you find a channel, and if this set has more than one element, you have a COM.
Yeah, on joins, if it has more than 0 elements, you have a COM. You can consume that only one that's in there.
Oh, yeah, in this set, you will pick one for a COM, right?
Bingo, that's right. Yep, just pick one.
Because it's one-to-one. But if you have persistence receive, then you will consume all.
Yeah, that's right. Yeah, and persistence is something I haven't really modeled very well yet. It's in there, and my my FFIs use it in a pretty hacky way for the moment, but there's no way to parse like persistent sends or persistent receives or anything like that yet. So this persistence was just added. Yeah.
Okay.
So for now, we're basically acting like everything's linear, but it's true that these couple special ones are not linear yet.
You mentioned linear, and I was just reading some parts of this Abramsky's paper, and I figured out that I didn't understand what is linear in raw calculus. You know, Greg was saying the variables are not linear, right? You can use it multiple times. But I realized that in this paper, it is written that when you find the COM event, this is like a linear, because you're consuming and that's it. You cannot consume it multiple times.
Oh, that's why they call it linear. I didn't know that.
Yeah, and then I realized the Isaac is explaining also, and he was telling this is like a linear band, and I was linear. What is linear here, right?
Yeah.
But then I figured out this is why it's linear.
So linear variables are variables that can only be used once.
Yeah, and this is like intuitionistic logic.
Okay.
But for interpretation for classical logic is a COM event with consuming channels.
Yeah. Okay. Nice. Yeah, I only knew that term. Like I heard a bunch of the Pyrofex people referring to the single arrow listens or the single exclamation point sends as linear sends and linear listens. And I just picked it up from there, but I didn't know that had to do with like linear logic. Oh, linear logic.
Yeah, me too. Also, I found it in BNF syntax. There is also like a written comments. This is like a linear band.
Yeah.
And I didn't know why it's linear.
That's great. That's great to know.
So,
yeah. Okay, so let's see. We've made our tuple space. We've made our registry, which basically isn't going to be used at all yet. The comment says it all here. Put all the FFIs in place. So like I had those 2 special processes. We've got to get those in the tuple space. So we just said like, go through all our FFIs. If they're a send star or a join star, well, if they're not, then like something went wrong because those are the only ways that you're supposed to be allowed to do like, you know, FFIs. But otherwise, in the non-error case, then we're just going to par into the tuple space, whatever that process was. It gets evaluated in the empty environment because it's top level right now, no bindings. And this is its process ID. So I is just my looping variable. So they're just going to be like the process ID for the first one is 0, and then the next one is 1. I'm just using integers. So, okay, good. So we've got all our FFIs in the tuple space, which in some cases is none. If you didn't pass in any, it could still be totally empty. And then we're going to give, oh yeah, go ahead.
So you're saying that this can be empty, but you want to put at least this standard output and standard error, right?
I'm trying not to assume that one wants to do that. So there's 2 ways you can create one of these. If you call the standard thing that I exported, that's that fresh function we were just looking at, and it does put in the standard registry entries and FFIs. But if you want something more pure, you don't need to put those in.
Okay, yeah, that makes sense.
But in general, probably you're going to want those in there. So, okay, fine. So this is all that Fresh really like did so far. It set up these variables, put in the FFIs, and now it gives you back references to several functions. Some of these are just ways to access the, the tuple space stuff. When I pass it through this map constructor again, it clones the, oh, I'm using immutable JS. So most of my data structures are immutable.
Cool, cool.
Yeah, the pure JavaScript objects obviously are not, but the maps and sets and things like that are all immutable. And so here I'm just cloning it and giving back a clone. This is basically like for writing tests and stuff.
And then this is like a really good example for using immutable.
Oh, nice.
You're using maps, which really are maps, right?
Yeah, that's right. They're not just JavaScript objects.
Cool.
Yeah. So, oh yeah, and so I should point out the distinction too. I don't feel like I've made this decision for final yet, but where I'm at right now is that collections of data that can grow arbitrarily and will be like updated throughout the run will use immutable JS data structures like maps and sets, whereas ASTs for my actual like row length terms are not immutable. Those are just regular JavaScript objects.
But in a sense, you will not mutate this object, so it will be immutable, right?
It's that's close to true, but it's not quite true. I'm gonna tack later on. You'll see sloppy stuff about like tacking on methods and things like that. Maybe once I get more confident in better ways to do those things, then I'll switch to immutable. But for now, that's what I'm doing.
Okay.
I should have exported this. I don't know why I didn't. Apparently, I haven't used it yet. This just you give it some term. It must be a fully concrete term, so it can't have like free variables in it. And then it just tells you whether that term's in the tuple space. So if you give it a send of either variety, then it just looks up the appropriate channel in the tuple space. And likewise with joins, if you give it any one of these things, ground or par, whatever, those don't go in the tuple space. Only sends and receives do. And then since we don't have like a nice type system that can tell me when I forgot to pattern match on something, this is what I've been doing to help me debug. And this has saved me a bunch because like, the first couple terms that I wrote were like send, receive, and ground, and I didn't have par, bundle, or new or something. So like I would forget to update certain parts of my code to include the new bundles once I added bundles. And then these will just give me like, instead of just a test failing in some weird way, it'll actually say like, hey dude, you forgot to update this function to handle pars or whatever.
This is the environment, right?
Yeah, no, we haven't seen the environment yet. This is all just digging through the tuple space. Yep. So environments are associated with individual receive processes. And basically what that means is that like, when you go to run a continuation, in general, there will be lots of variable mentions in that continuation. Some of them may have come from outside of the for itself. So like, imagine if I do this, new x in here for like y from @nil, then, whatever. So I could mention x in the body of this thing, but by the time this for gets put into the tuple space, this code is no longer around, right? Like I already evaluated this new, and only the for is going to go in the tuple space. Maybe let's make this like x plus y. So now
this x is like a free variable for this for. Right?
Yeah, that's right. If we only look at this part, x is a free variable, and so the environment needs to keep it bound. So here's what goes in the tuple space. We would have a thing that was like tag join, because this is the part that's going to go in, right? Every join has actions, and this one only has one action. And we'll figure out what to. It's not that interesting to type out the whole thing, but here's my only action. The channel's @nil or whatever. And then the body is. I actually don't have all of this done, but this would be something like an add expert or something like that.
Oh, I see. Okay.
And then here's the important part. Here's what I'm trying to get to. We tack on this part, the environment. And this environment will look like X tag unforgeable ID, and then, you know, I don't know what it's going to be, but something that was generated according to my random state. And so the beauty is when I go to execute this continuation, like, you know, for now I'm just jamming this thing in the tuple space, but at some future point it might be part of a COM event, and then I'll have to execute the continuation. And when I evaluate this continuation, I need to know what X was at the time when this for was written, and that's why I've kept it around in the environment.
So when you store this for continuation in a tuple space,
yeah,
then in that moment you are capturing X and store it with AST for in tuple space.
Exactly right. Exactly right. Oh, and this is an example of one of those times where I am actually mutating one of my JavaScript AST objects because I'm tacking on this environment property. Yeah.
This is very, very similar to what Quark explained to us, right? In his example,
yeah, it might be. I think it is. Yeah.
His state and he says the reader and state where he stores this context. Yeah, he called this context.
Oh, I did not fully understand that that's what he was doing. Yeah, that's
cool. Yeah, but in his code here, he's searching for a type, not for exactly name, which seems very, very similar thing to do.
Yeah. So.
Cool.
Okay, so I'm going to skip over is empty. It does what you think. It tells you whether the tuple space is empty. So, okay, right. So function deploy. This is one of the things that I exported, and I'll let you read the docs.
Cool.
So when someone wants to par in a term, they give you the term here, and they give you a seed for the random state. So I basically have a single number that's serving two purposes, and I think that's okay, and I'm not going to change it until I learn that I'm wrong. But the two purposes are, first of all, giving each term a unique ID, which is how I sort them into that prox map that is part of my tuple space. And then second of all, it's used to generate the random IDs of like more deeply nested ASTs that might be in there. So if I'm deploying something like a new or a for or something that has a body or a par, for example, each of the terms in that body are also going to need their random state, and it's calculated deterministically from this seed. So as you can see, yeah, go ahead.
You said that you're generating unique key for prox map.
That's right. That's right.
But prox map has a key, a name.
Let me go back to my README. So the prox map, the keys are these IDs and the values are ASTs.
Oh, IDs.
Yeah.
What are IDs? Unique IDs. This is not a name.
Its data type is like a uint8 array. It's basically just a sequence of bytes that can be put in and into a hash function, and I'll also get the same type back out of my hash function. So they're just numbers.
But you are converting your names to numbers, or?
No, it's not based on the names. This is not based on like what channel the thing is sending on. This is just, if I parred this send in directly, this is whatever seed I gave it. Or if it came from some, you know, deeply nested continuation, it's some deterministically calculated, like, you know, pseudo random, probably super insecure, like hash of its ancestors, the things in which it was nested in of their IDs.
And the reason you are doing this because you want to have flat map for all your names.
Yep.
You want to have a flat list.
Yeah, yep. One reason is that because by associating these unique IDs, it allows me to make this thing, which isn't so deeply nested like the other part was. And then the other reason I do it is because when we handle like new X in whatever, that X needs to bind to something. And basically what it's binding to is just a pseudo random number. And so that part I stole from Kyle's design, where each unforgeable ID is basically just like a pseudo random number.
Oh, okay, okay. So in a
So
sense,
from
this is like unforgeable names that you're
yeah,
storing the map of all of your unforgeable names.
well, yeah, but okay, so be careful. Every term has one of these IDs, whether it's a send or a par or an unforgeable variable or whatever it is. Every single term has one of these IDs. Now, if it happened, the unforgeable IDs are used, first of all, to identify this own term, like I'm doing here. But then they're also used to calculate the IDs of like future terms. So like the things that are inside this join's continuation, whenever this join comms and those things in the continuation move up to be ready to go into the tuple space, they're going to need their own unforgeable IDs. And their unforgeable IDs are going to be calculated based on this 567 from it, the mother join, plus, you know, whichever of these ones commed with the join.
Oh, sorry, my connection was.
Oh no,
Can
that's
you
okay.
please repeat?
Totally, totally. And in fact, it's good because I decided I want to do it with an example. So imagine I have this 4x from like at nil. And then what we're going to do here is at nil send 5. And then we're going to com it with at nil send 4 or something like that. So the 4 on line 1 and the send on line 5, those are both top level processes. So their like ID is going to be whatever seed I happen to pass in. So we could just pretend like this one's 1, 2, 3, and this one's 4, 5, 6. So they both go into the tuple space. They both have these IDs as we've specified. And so now imagine I want to execute a com event. And I say like, okay, row VM, execute the com of process 1, 2, 3 with process 4, 5, 6. And it'll go through and make sure that, first of all, they're both on the same channel, which they are, and that all the actions have been consumed, and there's only one, so it has. And they'll make sure that the pattern matches and 4 matches X. So that's all good. And once all that stuff is checked, now we have a com event. And so we're going to reduce to this state. Whoops, this is my downward facing arrow. We're going to reduce to just at nil bang 5. And so the question is, what is this process's ID? And it's some like pseudo random function of 1, 2, 3, and 4, 5, 6. Yeah.
Yeah, and you already done this? Do you have a code for this?
Yeah, I'll show you the code. It's super.
Oh.
I don't want to give you the impression that it's like cryptographically secure or very carefully thought out, but yeah. But
Okay. But I'm more interested in not the cryptographic part.
Yeah. Perfect. Me too. We're in the same place. Okay, so we'll sort of see this in more detail when we look at that part in helpers. But for now, what you need to know is that when you deploy a term directly, a top level term, its ID is just whatever seed you gave it. Like I said, eventually I want to hash those because I want them to all be like, 128 bits long and reasonably collision resistant and everything. But like for now, I just like knowing exactly what the IDs are on my term. So I haven't done that yet. And deploy basically just wraps this more detailed par in, and it sets up the environment with an empty environment. And the idea is basically like, when I, as a rhoxy programmer, go to par in a process like this, it's not correct to put in bindings already. Like, if I did at nil bang y and I tried to run this program, it shouldn't be valid because y is a free variable. And if I exposed this par in thing directly to the user, they would be able to precede that environment with y being bound to whatever. So I keep par in secret, and I expose deploy just so that I can make sure that whatever users deploy always correctly starts with the empty environment.
Oh, I see. Mhm.
So, okay, so anyway, here we are in par in. This is the real one, and I do this pattern match again. If you par in a ground term, that does nothing because those don't even go to the tuple space. If you par in a bundle, just unwrap it. The bundle tag only matters when we're pattern matching, and just par in whatever thing,
Is inside.
returned that proc. Yeah, whatever was inside. That's right. Sends. Okay, so here's the first time I call evaluate in environment. And the reason that I do that is because this is a recursive function. So we talked about how when you start, environment's always empty. So calling evaluate in environment when the environment's empty doesn't really do very much, but since this could be the result of a COM event, that environment's not always empty. So what this does is it goes through and it takes any variable mentions, like, variables that got parsed from what the user types, and actually replaces them with the proper ASTs that are bound to those variables in the environment.
Okay.
So for example, this is now valid, right? I could @nil bang x here, and x would be 4. So the AST for this thing is going to be something like tag send channel, the channel's @nil, and the message is going to be like tag free variable given name x. Well, after I run it through evaluate environment, then I no longer have free variable x. Now I have whatever x was actually bound to, like ground int 4. Yeah.
So in that step, you create substitution.
Bingo. Yep. This is where the substitution happens. That's right. And the other thing that it does is it tacks on 2 methods. So this is a little bit sloppy and mutation-y. So we do all the substitution I talk about, and then I also tack on a .equals method and a .hashcode method. And the reason that those are necessary is to make mutable objects work correctly with immutable JS library.
Oh, I see.
If you don't have those methods, then immutable JS just like treats them, I don't know, like reference semantics, right? If they're not literally like
the same reference.
Yeah, exactly. And that's not what I want. I wanted value semantics, and so I had to tack on those 2 methods.
Okay.
Yeah. Okay. So okay, great. So we're parring in ascend. Remember, that's where we are. We're in the function par in. The thing we're parring in is ascend. So we go ahead and add it to the prox map. And and there's a better way to do this that I recently learned, but I just haven't done it yet. And it's just like you were saying, like if there's already a send on this channel, then go into the sends map, dig out the set associated with this channel, and put in the new one. On the other hand, if there's not yet a send associated with this channel, then just add that key to the send set. So there's I learned recently that these immutable maps have an update function that would make this into a single line, but I haven't done that yet.
Oh, this is like an add or update.
Yeah, exactly. Exactly.
Oh, cool.
Yeah.
Cool. Good to know.
Yeah, totally. Join works mostly the same way. Here's one big difference though. We always, whenever we're processing a join, we always want to tack on that environment to the join so that we can use it more deeply.
Yeah, that was my question from the beginning. So you must infer environment from the parent scope.
Yeah, exactly.
But this is like
exactly what this does. Yeah.
Equal. You made it equal. So you didn't like infer. You just copied from.
Oh yeah, yeah. That might not be right actually.
I mean, you have recursive call, right? So is there an environment from the parent scope and then, or
this is the one that was passed in that came from the parent.
And this term dot environment is the current environment in the current of the current term, right?
Yeah, the join. So the join that I'm parring in, like the one that matched here, it doesn't have any dot environment yet. That property just doesn't exist because the parser doesn't give those. So here I create it, and I assign
I
it
see.
to whatever environment was passed in. Oh, this is right, actually. The places where we need to update it are when we're processing a new or when we're processing a com, because that's when new bindings happen.
Oh, yeah. The environment is not tuple space.
Yeah, that's right. Environment is different than tuple space. Yeah.
Yeah.
Right.
So you are updating the tuple space, but environment is just environment is really a system processes that you already have.
Yeah.
Space.
Environment is all the bindings. It's all the bindings that have happened. So let's do another example here. Let me make this a bigger one. We can do like for z from @nil. And I'm just gonna put that thing further in. So whenever finally this thing needs to be evaluated, it now has two variable mentions, right? And they both came from different generations of ancestors where they were bound. And so the idea is, like, when I first par in this thing, its environment will be empty because it's a top level thing. Then when it comms with something, when this 4 on line 1 comms with something, now this is going to be put into the into the tuple space. But it's going to have an environment where Z is bound to, 4 or whatever it was that Z commed with. So now we have this thing in the tuple space with an environment with Z already bound. And you have to have Z in the environment because otherwise Z would be a free variable in here. So then later, now the part lines 2 through 4 is in the tuple space. It comes along and comms with something different. So that's going to bind X. Like we can do this.
Mm. And you will eventually have an X and Z in the environment.
Bingo. By the time we get down to evaluating this thing, we're going to call evaluate an environment, this send, and the environment's going to have a binding for X and a binding for Z.
So the tuple space is a map, and environment is also like a map.
Yeah, totally. It's also a map, but it's a different map.
Yeah.
And here's one way to help keep this straight. There's a tuple space, right? Every row VM has one tuple space with a bunch of sends and receives in it. But environment is very much a per term thing. So every receive has its own environment attached to it.
And when you create, when you have a new creates environment, right?
Yeah.
This is the only thing that creates environment.
No, news and comms also.
And com.
Yeah, that's right.
Okay.
Yeah.
But the new creates directly.
That's right.
It's not some kind of operation that happens.
That's right. So when I go to par in something like this, well, in fact, let's look at it. This is not so bad, right? New X in X bang 4. So here's the top of my par in function. And we're going to match with a new. So here it is. So we're going to be in this case, right? So we start off with letting the new bindings be an empty map, and I'm about to go through and mutate the heck out of this thing. So for every one of the variables that I'm creating is new, because it could be many. And in my example here, there's only one. I only created X, but it could be new X, Y, Z, however many. So there could be a bunch of them. So we're going to loop through all of them. We give each one of them look, this is awesome. So in new bindings, we associate X, whatever it was, first X, then Y, then Z, with this sort of temp random value. Right now, temp random came from this. We're just hashing the random state. And so you can see every time I go through this loop, I take one more hash. So it's like a hash chain, right? I hash a thing, then I hash that hash, then I hash that hash. And that just gives me a chain of pseudo-random numbers. And those are what I'm using as the unforgeable IDs associated with those new names.
And can you show me random state?
Random state is what I previously called seed. That was kind of silly. So
okay.
Takes random state. Up here I called it seed.
Oh, I see. Okay.
Yeah. So it's just a uint8 array. And then, okay, so let's, down here at the bottom is something else we should show. I said, so let's match these up, right? Here's my case. So I finally, remember news don't ever go in the tuple space. So like, even though I'm in par in, I'm not gonna modify the tuple space at all here. Instead, what I'm gonna do is create all these new bindings, and then I'm gonna recurse with whatever the body of that new was. That's what really needs to be parred in. But now the environment is whatever it was to begin with. If it was top level, this part's empty, plus all these new bindings that we just made when we associated the new XYZ with all these random IDs.
This is when you're doing the merge, really.
Yeah, this is where I do the merge.
Of these environments.
Yeah. Yeah. And then there's a similar merge that happens in the case of comms, but that's down here in this execute comm function. Yep.
Cool. Mm.
Okay. Want to keep moving?
Yeah.
So here's execute comm. It takes one comm and does the reduction. And you have to specify which join you want to comm and which sends you want to comm. And in general, it'll be multiple sends because there's multiple actions in the join. So first thing I do is just look up the actual, so I'm passing in IDs here, like those numbers, like the 1, 2, 3 or whatever. So the first thing I do is grab the actual processes out of the tuple space. So now comm join and comm sends are an AST and a list of ASTs.
Yeah, you're getting from these maps.
Bingo.
The real processes. Okay.
Bingo, that's right. Now I call, wow, let's see. This might need a little bit of restructuring, but it works at least. So what I do is I get all the bindings that are gonna happen from this comm event, or false. So bindings is either gonna be a map like we just talked about, X is this, Y is this, or it's gonna be false. And if it's false, that means that the comm isn't gonna succeed, either because the patterns didn't match or because the channels weren't the same or something like that.
And you can get the bindings because you have environment directly connected to processes.
Yeah, well, specifically, there's an environment connected to the join. Well, to the join.
To joins. Okay.
Yeah. There's no environment connected to sends, only to joins.
I'm gonna have to go to another meeting. This is really awesome, Josh. I love this.
Oh, thanks, Jim.
I hope we continue this.
Oh yeah, totally. So when you leave, what happens to the recording? It just stops, I guess, right? But that's okay.
The recording stops. We're all ready.
What if I claim host? Then I can start again, right?
Yeah. Now I can make you a host right now, so that you don't want to have to put in the. There you go. You won't have to put in the.
Oh, nice.
You are hopefully I won't end the meeting again this time.
It's okay. We know how to start again.
And
bye, Jim.
Bye, Jim. Good chatting, man.
So if you want, so do record.
Yeah, we'll do.